Okay, so today we will go over an application of what we had done about the ideal Fermi gas. We will look at white dwarfs. Now, what do we mean by a white dwarf? If you have heard about the evolution of stars, you have a star, it burns a hydrogen. The hydrogen creates heat and also pressure, which balances the gravitational pull. So as long as the star is burning hydrogen, it can have a stable equilibrium. But eventually it runs out of hydrogen, so there's no more heat generation. So there is nothing to balance the gravitational pull. So the star starts collapsing. So the pressure increases, but now it's mainly helium. There will be some fusion of the helium nuclei. It can go up to iron. But there will be less energy produced, less heat produced, less pressure produced. Eventually the star will collapse. So, but the star is made up of mainly fermions, and we have seen that there is a fermionic pressure. Now the question, what happens in white dwarfs is mainly the pressure of the electrons can balance the gravitational pull. The electrons are moving quite fast. They will have a high pressure. It might be enough to balance the gravitational pull, and that's the system that we will be looking at. Now, of course, it's a complicated system. You have to also include all the various nuclear physics effects because of the fusion of the nuclei, plus you have to take into account the gravitational forces, etc. But we will come up with a very simple model here. Just a box without any walls, by the way, a box that is stable due to its gravitational pull, and what will be the pressure? And can we determine the size as a function of the mass? That will be the purpose. Now, just to give some numbers, the mass of a typical white dwarf is 10 to the power 33 grams of mainly helium. How do you measure the mass of a star that is, I don't know how many light years away?
With the trajectory of things that move around them.
You can, if you can see them, then that would be a way of, you measure the radius, you measure the period, the relation is determined by the mass of the object. Yeah. The amount of light they emit, it also gives you an idea about the nature of the star, but then it's basically a model. If your models work fine, if you are confident with your models of how the structure of the star, then yeah, that also gives you an idea. The density is around 10 to the power 7 grams per centimeter cubed, so this is like 10 tons in 1 centimeter. This is the density. The temperature is 10 to the power 7 Kelvin. These are the numbers I just looked up in your book. And remember, the ionization energy typically is of the order of electron volts, which is 10 to the power 3, 10 to the power 4, which is much, much larger than the ionization energy, the ionization temperature. So we can safely say that whatever atom is in there, it's completely ionized. It will be mainly helium. So all the helium is ionized. So for each helium atom, you have 2 electrons. If you know the mass, the helium nuclei has a mass of 4 mass of the proton. For each helium, you have around 2 free electrons. This is the number of atoms, number of electrons you have. Now we need to determine the equilibrium size for this mass. On one hand, we know that it will have a pressure. Before continuing that. Now, we know the number of free electrons. We know the density, the mass density. And remember what was the Fermi energy? The Fermi energy is some coefficient times n to the power 1/3. N being the number density, n over v, or we can write this as n over m times m over v Now, m over n is around 4 mass of proton. You see the number of electrons is given by this number. Now, 2 mass of the proton. And m over v is just the mass density. Sorry. So we know the number density of electrons, and which turns out to be, which gives me the Fermi momentum to be around 10 to the power minus 17 gram centimeters per second, which turns out to be of the order of the mass of the electron times the speed of light. Now, what does this tell me? Well, this tells me that electrons are relativistic. You see, the average energy is determined by the Fermi energy. Although some of them will have a very low energy, the dominant one, most of them will have an energy of the order of, will have a momentum of the order of the Fermi momentum, and Fermi momentum is almost equal to the rest mass times c of the electron. So this is only possible if the electrons are moving very fast. Why is this important? Because this tells us that the energy momentum relation for these electrons inside the white dwarf is a linear relationship. So if you remember how we obtained the Fermi momentum, n is, well, here we assume the Fermi momentum to be n to the power 1/3. This was the non-relativistic case, but now we know that it is relativistic. We need to make necessary corrections. And the total number will be g, whatever the degeneracy is. We are talking about the electrons. It is 2 v d cube p theta epsilon p Fermi minus p. No, sorry, this p Fermi expression is still correct. This is equal to 8 pi v times p Fermi cubed over 3, which tells me that p Fermi is 3 over 8 pi, density to the 1/3. So this is actually what I had used. And I can also obtain the Fermi energy, which will be p Fermi times c. And once I have the Fermi energy, there is a corresponding Fermi temperature. And the definition of Fermi temperature is epsilon Fermi divided by K, which is of the order of 10 to the power 10 Kelvin. So what does this tell me? You see, this tells me that the electrons I have are relativistic. Since T over T Fermi is of the order of 10 to the power minus 3. You see, Fermi temperature is 10 to the power 10 Kelvin. The temperature of the white dwarf is 10 to the power 7 Kelvin. So T over T Fermi is 10 to the power minus 3, which is much, much less than 1. This is a cold, relativistic Fermi gas. See, although its temperature is 1 million Kelvin, it's a cold system. Which means the Fermi-Dirac distribution is almost a step function. Now, what is the pressure? You see, if you remember, we had looked at the motion of the particles with an arbitrary distribution before. And we had seen that the pressure is actually given by the momentum times U average of this quantity times 1/3 n. 1/3, yeah. Now this, if you don't remember, what we had done was we had assumed the wall. There was these particles colliding with the wall. If this was the z direction, and the amount of momentum transferred by this particle was delta p was 2 mpz. And then we said that n of v, we just called it the or f of v, the velocity distribution, whatever distribution we have. And then we said this much momentum is transferred by particles, let's say here, if I assume a cube, I have n times dv particles within this cube. Some of them will move towards my wall, some fraction. This is dv within a volume, let's say d cubed v. This is the small v is the velocity. The particles whose velocity is within this d cubed v volume in velocity space will move towards my surface. And they will impart a momentum given by this expression. So I just need to multiply this one, n times dv times d cubed v, and summed over all v. Now d squared v, dvz. Of course, dvz should be from 0 to 0, infinity, etc. If you do all this derivation, this is, if you review that derivation, this is what we obtain at the end. We have the momentum transferred, and this volume has a length, let's say v times dt. dv is just dA dot v dt. This is my dv. This is all the volume, the relevant volume. And so if you divide by, let me write this delta t. So this is all the particles within this volume will hit my area dA here within a time delta t, and they will give a momentum 2 mpz. And hence I get the pressure. Remember, pressure is force divided by area, force in the z direction. So this will be delta p total divided by area delta t. Delta p total is the total momentum transferred, which will become d cubed v. For, of course, vz should be larger than 0. Only the particles moving towards my wall will collide with the wall, of 2 mpzn and then here I will have Vz dA delta t divided by dA delta t. Let me write the small force a very small amount of force acting on a very small amount of area. So these, also there's the F distribution of velocities. The A's and T's, they will cancel. So what I will have as pressure is d cubed V integrating over Vz larger than 0, F of V 2m Pz and, sorry, there's no m2pz. And Vz. Now, if f of v depends only on the speed, not the direction, this integral is symmetric under Vz goes to minus Pz. So the same integral is the integral over all V, f of v, n Pz Vz. This is nothing but n times the average of Pz Vz, which is n times average of Pv cosine squared theta. And the average of cosine squared theta is where we get this 1/3. So that is how we get this pressure of my system. U is V, the velocity. And this derivation, by the way, doesn't assume any specific form of the distribution of the velocities or the particles. So whatever the particle distribution, the velocity energy distribution is, this is the pressure of my system. Now here we have a thermal distribution. So the pressure at 0 temperature will be, well, on one hand I can calculate this average, let's say, 1/3 n I can integrate over all angles. That will give me a 4 pi. I have dp p squared vp. Now the question is, what is the velocity of these particles from 0 to p Fermi? The velocity is the derivative of energy with respect to momentum. Remember Hamilton's equations of motion. Q dot is the derivative of the Hamiltonian with respect to momentum. Q dot is what we call the velocity. And energy of these particles, of course, this is for the ith component. Energy of these particles is P times C, which is square root of px squared plus py squared plus pz squared C minus mc squared. This is the energy. Pc, well, they are relativistic, so we can just ignore that one. Sorry. This is also correct, but we can be better than that. This is p squared plus m squared under the square root. If you like, you can set the m equal to 0 afterwards, which will give me, okay, p over m divided by 1 plus p over mc squared. So this is the velocity. So P0 would be just 4 pi over 3h. There's also 2 because of the degeneracy. And dp p squared p over m divided by squared from 0 to p Fermi. Why from 0 to p Fermi? Because it's a cold system, and I'm practically taking the 0 temperature limit of this pressure. It won't be much different from the 0 temperature limit. Now, I will skip how do you evaluate this integral. I will skip some steps. Typically, what we do is we define the u as c times tangent hyperbolic theta. Velocity is just like a rotation angle in Boost, but an imaginary rotation angle. So that is what this theta is. So for those doing particle physics, this is the theta is called the rapidity. One of the experimentally measured parameters. So P turns out to be mc sine hyperbolic theta. Let me jump steps. We have the total number. I can express total number in terms of this theta f, which is mc p Fermi is mc sine hyperbolic theta f. I'm just making some change of variables. At the end of the day, I will obtain, when you evaluate that integral, etc., you obtain P0 is some function of x, where x is defined as sine hyperbolic theta f, which is 3n over 8 pi 1/3 h over mc. Now, just forget about all the derivation. The important thing is P0 is a function of x, or P0 is a function of the density. If I know the density, I know the pressure. That's the crucial thing. Now I will use one more condition. If the system is in equilibrium, you see, there I have two effects. One is the gravitational pull. The other one is this pressure is pushing everything out. So there should be if there is an equilibrium point, it should be such that if you push it out a bit, it should come back. If you push it in a bit, it should come back again. And if you consider the n, it should be some kind of an extremum point. It will be an extremum of the energy. I mean, every system tries to minimize its energy in equilibrium. So the only way that it will come back to this equilibrium volume, whether you push it inward or outward, is if the energy is is a minimum when it's in equilibrium. That will be the definition of equilibrium. If we change the volume slightly, if we change the radius slightly, the energy should increase, should not change, sorry. The change will be quadratic in the change in the radius, not linear in the change in the radius. So that is what I would like to calculate. I would like to show that this is equal to 0 for the system. Now, what is dE? Well, there will be a change in the energy from pressure, which will be just minus P0, which is a function of n or x times dV. But dV is just V is 4 pi over 3 r cubed, so dV is just 4 pi r squared dr. This is the change in, if the radius changes by a slight amount r, this will be the change in the energy due to the pressure. Well, it also has a gravitational energy. The whole system, it has a gravitational potential energy. And gravitational potential energy is, if you remember, well, this is a typical question in the freshman course. You have a mass m, mass uniformly distributed. What will be the potential and gravitational potential energy of the system? Well, the gravitational, just look at the units. It will be proportional to the Newton constant. The force is proportional to Newton's constant. It should be proportional to the mass and inversely proportional to r. In fact, the only quantity that will have the unit of potential energy that you can construct from these quantities will be this one. And if you remember all your computations, what you will see is that the gravitational potential energy will be some multiple of this. 5/3, 3/2, it will depend on the mass distribution. Let's just put a number alpha. Can this be the potential energy? Gravitational potential energy. Alpha is just some number. It will depend on the mass distribution of the star. Now there's something fundamentally wrong with this expression of the energy. Where is the minimum of this energy? Well, the gravitational potential energy tries to attract it, so it will try to squeeze this radius. The minimum should be at small radii. So there's a minus sign. And without that minus sign, you can say that that's definitely wrong. Typically, this will be the energy. So the change in the gravitational energy of the system, due to a very small change in the size, will be just alpha Newton's constant m squared over r squared dr. The total change in the energy, there will be a change due to the pressure given by that expression, minus P0 and 4 pi r squared. And there is also an increase in the energy due to the gravitational attraction. dr, this should be 0. In equilibrium, this is 0. So we have minus P0 and should be equal to, or P0 n should be equal to alpha g n m squared over 4 pi r to the 4. Now, I will not write down this expression again. It's a terrible looking expression. But essentially, both sides depend on mass and the radii. So this will give me a relation between the mass and radii, or if you like, radius as a function of mass. Given the mass of the neutron star, you can identify what should be its radius. Now, explicit expressions are not possible, but certain limits, for example, if the radius is larger than 10 to the power 8 centimeters, well, why is the 10 to the power 8 centimeters? That is mainly the numbers I had quoted at the beginning of the lecture for the mass, etc. In this limit, x is much less than 1. And you can actually determine the radius as a function of mass. What you get is this expression. So the larger...
Indicates that this is the expression indicates that r is larger than this one?
Yeah, if r is very large or x is very small, you see, we can express everything in terms of what we call the x, the Fermi momentum. If x is very small, you can just work out all the algebra, etc. This is what you get. R is proportional to the inverse cube root of the mass of the object. Well, this is expected. The larger the mass, the smaller the star will be. You will be compressing it more, the gravitational force will be more, you will be compressing it more and increase the pressure, and eventually, if the pressure becomes large enough, it will balance the gravitational pull. You can look at the other extreme. When r, you see, let's say that you are increasing the mass. As you increase the mass, the radius gets smaller and smaller. Eventually, it will be smaller than 10 to the power 8 centimeters. If r is less than 10 to the power 8 centimeters, that means your mass has become already very large. You get a radius which is proportional to 1 minus m over m0 to the power 1 over 2, m0 given by some number. It's this number over here. Well, what does this tell me? Well, you see, we have a star. Let's start with from a small star. For a small star, then a small but still the radius is much larger than 10 to the power 8 centimeters. If you increase the mass, the radius becomes smaller and smaller. Eventually, the radius will be much smaller than 10 to the power 8, and the radius, in terms of the mass, radius is given by this expression. But now we have a problem. If m is larger than m0, there exists no solution. In fact, when m is equal to m0, you find the radius that is 0. The gravitational force is so strong that it has to compress the star to almost 0 size so that the Fermi pressure will be able to balance the gravitational pull. Before becoming an object of 0 size, it won't be able to balance. But what happens if mass is larger than that? Well, the gravitational pull is so strong, practically the Fermi pressure of the electrons can no longer balance the gravitational pull. So it can no longer be a white dwarf. What will happen next will be the electrons will be crushed. Well, they will combine with protons forming neutrons. So eventually the pressure due to neutrons will be much larger. And it might be that the pressure of neutrons might be able to balance the gravitational pull. If they do, then we end up having a neutron star. But of course, during this process, you have all this fusion of the nuclei, which release energy. You can obtain supernovas, etc. Now, what happens if the pressure of the neutrons is not enough? Well, due to the gravitational force, it will keep on compressing the star. And maybe there will be it might be balanced by the quarks. You get quark matter, but the pressure of the quarks and the neutrons, they are not so different. So if beyond the neutron star, there is nothing to prevent the collapse of the star. And hence you end up having black holes.
Like for this to happen to a star, it has to, somehow accumulate mass to begin with, right? Just getting hot doesn't do it.
Just getting
hot, just being.
You say this is not hot. This is cooling down. That is what's causing the problem. So initially it's hot.
Being hot makes it like more pressurized.
Yeah. It increases the pressure. Here we are looking at the zero temperature pressure, which is if it fails to balance the gravity, then the star just keeps on collapsing. If it is hot, then it will probably stay there. If it keeps burning fuel, burning hydrogen, then it will stabilize the gravity. Because if it collapses further, that means there will be more fusion, there will be more heat produced. And eventually it balances for some time. But larger the star, the faster it will burn fuel. So the larger you start with, the larger a star you start with, its lifetime will be shorter. Smaller stars will probably live longer than larger stars. Because large stars have a large gravitational pull, and hence you need a larger pressure, which will come from a larger heat temperature. Once the star burns out its fuel, this is what we are talking about here. It becomes cold. Now, 1 million Kelvin, but still cold relative to its Fermi temperature. And then we have the Fermi pressure of the electron gas. But that also has a limit.
So this eventually happens to every other star?
Yeah. I mean, the first stop is a white dwarf. When the star burns out its fuel, the first stop would be this white dwarf.
star if it is?
And the limit is not far from the mass of the sun, by the way. The sun will become a white dwarf, and, but it won't become a neutron star. Any questions about these white dwarfs? So do we have any energy left for Ising model? One, yes.
I think
Sure, why not?
I repeat, these are Ising model. These will not be included in the exam. Just try to enjoy it. Now the problem is, in this course, we never studied interactions. We always look at non-interacting systems, ideal gases. Now that is one of the shortcomings of this course, but I think for a must course, this is more than enough. But still, I wish we had an elective statistical physics course which will continue with the future topics, the remaining topics. Now, Ising model, initially it was constructed basically to explain ferromagnetism. So what you have is, you have a Hamiltonian. You have the spins. The spins will be interacting with each other, let's say sigma I, sigma j. Sigma i's can be plus or minus 1, the simplest case. So if you just imagine various sites, at each site you have some spins. If both spins are what happens in a ferromagnet is the spins tend to align in the same direction. Spontaneously they align in the same direction. So that means that when the spins are aligned in the same direction, the system has a lower energy. So that is, if both sigma I and sigma j, they are nearest neighbors, let's say, if they both have, if they are both plus 1 or they are both minus 1, the system has a negative energy. So that is why we have minus j. And you sum over nearest neighbors, whatever that nearest neighbor means. And then you can, if you like, you can also add a magnetic field term, sigma I. And again, I repeat, sigma I and sigma j, they can take two values plus or minus 1. This is just a classical example. There are no operators, nothing. And, well, it looks quite innocent. But this system, although it was initially motivated by spins, it's quite general in the sense that, for example, a comment.
This was with paramagnets, right? You said.
Well, it depends. If J is negative, this becomes a diamagnet. If J is positive, this is ferromagnet. Now, ferromagnetism is kind of an extreme case of paramagnetism, if you like. Now, paramagnetism is in fact mainly related with this part, whether the spins try to align with the magnetic field or in the opposite direction. This interaction part is what makes it a ferromagnet. Because if J is positive, what it will do is, well, in fact, if J is negative, this is not a paramagnet, it's an antiferromagnet.
J is positive.
If J is negative. J is usually positive. What will happen is, you see, we had already studied this system for quantum mechanical systems, quantum mechanical spins. And we had this paramagnetic behavior. But we didn't have this term. What that term does is, even in the absence of any external field, this will push all the spins to be aligned in the same direction. That is the ground state. Which direction? Arbitrary. It will just choose a direction, and all the spins in the ground state, all the spins will be in that direction. This is also sometimes called spontaneous symmetry breaking. Why? Because every direction should be equivalent without B, without the second term, without an external field. All directions are equivalent. So in principle, my system could be pointing in any direction. But at the ground state, it just chooses one direction randomly. So now my system is no longer has that symmetry. It's only pointing in one direction. It had spontaneously broke the symmetry. This is also what happens in Higgs mechanism.
Isn't like Earth's magnetic field always there to just affect them all the time?
Yeah, in a realistic case, yeah, there will be a external magnetic field, and hence they will, if you create such a system, it will be affected by the Earth's magnetic field to some extent. There will be the temperature which will try to cancel that effect. But this model, this very simple model, you can also apply to, let's say, impurities in crystals. You can say +1 will be there is an impurity at that site, -1 would mean there's no impurity in that site. Or you can say that if you have a surface, you can absorb gases on the surface. Again, +1 might be there's an adsorbed molecule, -1 there's no adsorbed molecule. So we can generalize this model to other systems, not just only spins. But we will always be saying spins. Now, this model is easy to solve, let's say, in one dimension. Let's look at the one-dimensional case. Well, there's no phase transition there, so in that sense, that it's boring. But let's try to solve the system. We have the canonical partition function. The microstates will be summed over all sigma i's over ±1. All of those values. And we have e to power minus beta minus j sum over nearest neighbors sigma I sum over j sigma I plus 1 minus b sum sigma I. This is my partition function. Well, in one dimension, these are my sites. The nearest neighbors is just the next site. So that's why I have I and I plus 1 there. Now, I will first define an operator P to solve this problem. Like, how can you see? Well, we cannot see the solution straight away, but I think it was the I think could solve the one-dimensional case. Just the solution was just define this matrix with the matrix elements. This matrix element, or let me just reverse them. This will be defined as e to power beta j sigma I plus 1 minus b over 2 sigma I plus sigma I plus 1. So that it's symmetric. What I did here is h, in the one-dimensional case, h is given by minus j sum over I sigma I plus 1 minus b sigma I, which I also write as minus j sum over I sigma I plus 1 minus b over 2 sum over I sigma I plus sigma I plus 1. I'm summing over all I. Now, I will also assume I have I goes from 1 to n. I have n spins such that sigma n plus 1 is, I define it as sigma 1. And each possible set of sigma I will give me a new state. So what is my Q? Sum over sigma 1 plus 1 minus 1, sum over sigma 2 of sigma 1 p sigma 2, sigma 2 p sigma 3, sigma n p sigma 1. I have n plus 1 is equal to n. But you see, if I sum over sigma 2s, this is just matrix product. Sum over sigma 2 this is just identity, if you like, in the bracket notation. Well, I can do the same, the sum over all sigma i's, but that would give me sum over sigma 1 p to the power n sigma 1. Now, if I sum over sigma 1, this is nothing but trace of p to the n. And p, let's say p plus plus, it has 4 components. This is the definition of p over here. Now, p plus plus will give me e to power beta j minus b. P minus minus is the same. No, not the same. P minus minus is e to power beta j plus b. P plus minus is e to power minus beta j. And P minus plus is again e to power minus beta j. You see, when one is plus one, the other one is minus, their sum is 0. And this factor is minus 1. So this is my P matrix. It's just a 2 by 2 symmetric matrix. You can determine the eigenvalues. Let's say lambda 2 is the larger eigenvalue. So trace of p to the n is just lambda 1 to the n plus lambda 2 to the n, or lambda 2 to the n, 1 plus lambda 1 over lambda 2 to the n, which is lambda 2 to the n. Since I assume lambda 2 to be the larger eigenvalue, lambda 1 over lambda 2 is less than 1. A number less than 1 raised to the power of 10 to the power 23 is 0 for all practical purposes. So a trace of p to the n is nothing but the larger eigenvalue raised to the power n. Well, I will not do the derivation, but well, 2 by 2 matrix, you can find the eigenvalues of a 2 by 2 matrix. Take the larger one, whichever one that is. Lambda 1 to the n gives you the trace of p to the n, and q is nothing but lambda 2, the larger eigenvalue, raised to the power n, and practically we are done. If you want to calculate the average energy, take the derivative with respect to beta. If you want to calculate the magnetization, take the derivative with respect to B. It's solved. So I will just skip this case. Let's look at the 2D case. Well, thanks to Onsager, we have solutions of the two-dimensional case also now. I will not go into that. Basically, I also don't know the exact derivation, but there are some nice ideas to approach this problem, at least in certain limits. So what is the partition function is the same. This is our partition function. I will consider the free field case. Which is equal to product over nearest neighbors of e to power beta j sigma I sigma j. So now this is sigma I sigma j. Now every atom doesn't need to have one or two nearest neighbor. It will in general have four. If you have a, let's say, a square lattice, if you take any one, its nearest neighbors are these ones. So there's a 4. If you, I don't know, if you have a triangular lattice, made up of triangles, you see this site over here has 6 nearest neighbors. And that is usually denoted by Q, just a number, determining how many nearest neighbors it has. Now we will be looking at high temperature and low temperature limit. Let's say X or K is equal to beta J. K is much, much less than 1, means T large. And K is much, much larger than 1. This is T small. These are the large and small temperature limits. Now let's look at the large temperature limit. Now first let me look at this number. Now sigma I, sigma j can be plus or minus 1. Those are the only two options for sigma I, sigma j. So this number is equal to e to the power beta j if sigma I, sigma j is equal to 1. If sigma I, sigma j is equal to minus 1, it is e to the power minus beta j. Now let me try to write it slightly differently. This is e to the power beta j plus e to the power minus beta j over 2 plus e to the power beta j minus e to the power minus beta j over 2. And similarly here, this number is e to the power beta j plus e to the power minus beta j over 2 minus e to the power beta j minus e to the power minus beta j over 2. So again, the same number. If sigma I, sigma j is equal to 1, that number is equal to cosine hyperbolic beta j plus sine hyperbolic beta j. If sigma I, sigma j is minus 1, that exponent is given by cosine hyperbolic beta j minus sine hyperbolic beta j. So whatever the value of sigma I, sigma j is, that number is cosine hyperbolic beta j plus sigma I sigma j sine hyperbolic beta j. So I have this expansion. Well, you could see that there had to be such an expansion also by looking at the expansion of e to power beta j sigma I sigma j, which is beta j o to the power n divided by n factorial sigma I sigma j to the power n. Remember, sigma I squared and sigma j squared, they are just 1. So this is equal to sum over n even e to power beta j to the power n over n factorial plus sum over n odd beta j over n factorial beta j to the power n times sigma I sigma j. I just Taylor expanded the exponent. Odd powers of sigma I sigma j is equal to sigma I sigma j. Even powers are equal to 1. So that's the only thing I use. Then of course you have to see that these sums are just cosine hyperbolic and sine hyperbolic. They are Taylor expansion. So this I can, by the way, also write as cosine hyperbolic k times 1 plus sigma I sigma j, no, sorry, cosine hyperbolic, yeah, k sine hyperbolic sigma I sigma j times v, where v is sine hyperbolic beta j. Well, up to this point, I didn't do anything. I just rewrote my partition function, that's it. There is no approximation, but this goes to 0 in large T. In large temperature, beta is very small, beta j is very small, so this sine hyperbolic beta j is very small. So I have a small parameter at large temperature. Now let's go back here. Q. Sum over all possible values of sigma i's, product over nearest neighbors of cosine hyperbolic k times 1 plus sigma I sigma j v. How many nearest neighbors do I have? Well, let's go back. If I have n sites, each site has q nearest neighbors. The number of nearest neighbor sites will be 1 over 2 times n times q. Do you see why 1 over 2? Well, each one of these atoms have q nearest neighbor sites, so n times q. But keep in mind, n times q counts this nearest neighbor interaction twice. One, because it's a nearest neighbor of this one. The other one is the nearest neighbor of that one. So that's why I have to divide by 2. So this is equal to 1 over 2 n times q. Well, in your book, it shows it with this curly n. And then I have sum over these things of product of the nearest neighbors of 1 plus sigma I sigma j v. This is equal to 1 over 2 n times q. Let me try to write down that product. Oh, sorry, I forgot a cosine. This is not a... let me define this curly n as 1 over 2 nq. You see, each one of the nearest neighbor interactions has that cosine hyperbolic to the power of this curly n. Well, how do you expand the product of sums of matrices? Well, I can take the 1 from any one of them. That will give me a 1. Then I can take the term sigma I, sigma j from one of them and take the 1 from all the other matrices. So for each such parenthesis, I get such a term. Well, this is just the sum of the nearest neighbors. I can pick up sigma I, sigma j from 2 of the parentheses that I'm multiplying out. So that will give me sigma I, sigma j. Let me say sigma k, sigma l. But since there are 2 different parentheses, I and j should not be equal to k and l. And of course here I have a v, here I have a v squared. Of course I have higher order terms. Now what do I have? I'm summing over all these sigma i's, remember. Sum over, let's say, sigma I of sigma I. What is this? Plus 1 plus minus 1, 0.
But do they have to
Hmm?
come?
They have to come in pairs.
Yes, but like as far as I understood with this, like qi and qj, like this, I'm sorry, sigma I and sigma j, all the sigmas are just like random things.
Yeah. Well, I mean, they determine my microstate, if you like.
Can't
So-
they all be one?
You see, for a specific state, you see, all sigma i's being equal to plus 1. That is one of my ground states. All sigma i's equal to minus 1. That's another ground state. These two are degenerate in the free field case. But what do we do here in the partition function? What do we calculate? We sum over all the microstates. That is the definition of the partition function. At a given temperature, the system will not be in the ground state, or in fact, the system will not be in one particular state. So I have this statistical averaging. The partition function will be just the sum of all these exponential factors over all microstates. That is what I am doing here. And my microstates are determined by the values of these sigma i's. Each set of sigma I values, specific set, is one microstate. But I'm summing over all microstates. So sum of sigma I, if any of these sigma I, if any of these sites, the sigma of any of those sites appear only once, there is no contribution. The sum will be 0. I can get non-zero contribution from here, for example, if j is equal to k and l is equal to I. But that won't work because j and k will be different, should be different. I'm just summing over all different nearest neighbors.
No contribution from any of this. Or what?
We already have a condition. To receive a contribution, I should have each one of those sigma i's appearing twice. You see, let me draw a square lattice. Now, let me just connect these sites. So if this is the I side, this is the J side. That line essentially denotes sigma I, sigma j. Let's just make this identification. That line connecting those two dots, nearest neighbors, are my sigma I, sigma j's. Now, if I want to have a non-zero contribution, I should have two lines connecting to j, side j. So there should be from somewhere else. Remember, I have all these higher order terms, multiples of many, many terms. So if I have such a contribution, sum over sigma j will not give me 0. But still, sum over sigma I will give me 0. So unless there is another sigma I coming over from some other link. These are links. Well, let me consider this case. Well, this will give me a non-zero contribution because all the sigmas appear twice. I say I, j, k, l. This term corresponds to sigma I, sigma j from this link. This link brings me sigma j, sigma k. This link brings sigma k, sigma l. And this link brings sigma l, sigma I. This is one contribution. How many links do I have? 4 of them. So this is essentially a contribution of the order of v to the 4. Because remember, this is a link. Each link, sigma I, sigma j, comes with a factor v. The first contribution is not from v squared. There won't be a contribution. In the square lattice case, there won't be a contribution at v to v cubed. There will be a contribution at v to the 4. In the triangular lattice case, you will have v cubed contribution. So here you also see that the lattice also has a significant effect on what you have. Do I have other contributions? Well, sure. For example, I have a contribution corresponding to these links. How many links do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The red one is a contribution of the order of v to the 12. Not of the order of, that is the contribution of that term. Now this term, let's say this term will contribute, I also have a summation over all ij, over all sigma i's, sorry. That is just, that product is 1, whatever the values of sigma i's are, so the contribution is actually I, j, k, l to the 2 to the 4. Right? I have 2 to the 4 possible cases of sigma I, sigma j, sigma k, sigma l. Each contribution is 1, so I end up having 2 to the 4. Well, I would probably write this as over 2. So on the lattice, given each closed loop, I know the corresponding contribution. And keep in mind that large T limit, V is small, so it would be enough to keep the leading correction. So for example, for a square lattice, it is V to the 4, the first correction. So we have ZQ is equal to cosine hyperbolic K to the N. No, sorry, K to the N 1 plus v divided by 2 to the power 4 plus higher order terms. And v is tangent hyperbolic k. And this n is 1 over 2 n times 4. For the square lattice, q is just 4. And as your friend pointed out, we also can have this rectangular lattice here. And the smallest closed loop you have just goes around the triangle. So the corresponding contribution will be v over 2 cubed. Sorry, let me calculate this overall coefficient properly. So here I have a sum over ijkl. I have this summation over ijkl. And then a summation over sigma I. Now, sum over ij, sigma I, sigma j, sigma k, sigma l will give me this 1 over 2 factors. How many such closed loops I can form? Well, just pick one corner. If you pick lower left corner can be at n different points. So you get an additional factor n. This should be the number we have. Because basically if you have every closed loop will give you a contribution. This contribution will be the same as this contribution, will be the same as this one, etc. So if you just determine one corner of this square, that corner can be anywhere among these, well, less than n, but the difference will be very small, n squared, sorry. No, you have n sides, so you have n. Now, the reason why I wanted to mention this Ising model is essentially, okay, you have these interactions, but whenever you have these interactions, okay, on one hand you can have all these matrix product summations, infinitely many terms, but usually what we do is we end up having such diagrammatic representations of different contributions, which are easier to remember. You just count the number of closed loops you can construct, having a given number of links. And then you know how to calculate basically the corresponding contribution. If you have one loop with L links, the corresponding contribution will be this one. No, sorry, it's not V over 2, it's 2V to the 4. This is one limit, the high temperature limit. Now then, of course, there is a question of the low T limit. I will just mention it, and I think that's enough. For the low temperature limit, let's go back. Again, we are calculating this term. Now the trick we had in the previous case was we identified e to power beta j sigma I sigma j with cosine hyperbolic k times 1 plus sigma I sigma j v, where v was the tangent hyperbolic k and k being beta j. So at high temperature limit, k is small. If k is small, v is small, so v is our expansion parameter. We just take the first correction in v. Now, if you go to the low T limit, beta j is very, very large. So in the low T limit, what we expect, what this tells us, beta j is very, very large, tells us that the main contribution to this sum will be from the terms sigma I. All sigma i's are either +1 or all sigma i's are from -1. They have a very large contribution. Now, if you factor that out, there will be, let's say, Q is equal to e to power beta j n. This is the contribution from the ground state. This curly n. Remember, ground state energy is when all the sigma i's are either plus or all of them are minus, and we have this much nearest neighbors, and each has an energy minus j. This is the ground state energy. Then we can look at the corrections. The ground state, there will be this one, plus e to power minus the first excited state minus the ground state, plus higher order terms. Now, what is the first excited state? Well, one of the spins flip sign. Let's say that, again, we have this square lattice. Let's say all of them in the ground state are positive. Let's pick this ground state. And let's say that the first excited state will be one of them flips sign. So this becomes negative. So this is the first excited state. The second excited state will be you have two spins flipped up, two neighboring spins flipped up, let's say. The third excited state will be two non-neighboring spins flipped direction, etc. So let's see, what is the energy of this system relative to the ground state? Well, there is when I am summing over all nearest neighbor interactions, there is a nearest neighbor interaction here, another nearest neighbor interaction crossing that line, another neighboring interaction here, another neighboring interaction here. So I have four neighboring interactions which contributes plus j rather than minus j. So this first contribution here from this closed loop is for j. This is the contribution from the first excited state. And remember, k is beta j, which is much, much larger than 1 at the low temperature limit. How many such states we have? Well, if we have n sites, that flipped spin can be anywhere on that n sides. So this will be the first correction. I have n. The degeneracy of the first excited state will be n. Now the next excited state will be not one flipping, but two of them flipping. But keep in mind that if the two of them are not nearest neighboring sides, let me also write that down. If I have, let's say, if this one flipped sign, let me also look at that state. Now, this excited state, what is its energy? Well, there's a different nearest neighbor interaction there, here, 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 and here. So I have 6. The energy of this state is 6J above the ground state. Now, if I look at this one, here I have all these 4 have different nearest neighbor spins. And similarly here, all of these nearest neighbor spin interactions are of opposite parity. So the energy is 6J. So although these two states have 2 spin flips, even they don't have the same energy because above one, I have a single connected closed loop. Here, I have an open loop. Well, I practically obtained a similar expansion in terms of closed loops. So I can imagine these closed loops as separating regions of one spin from the spin of the other spin. And the length of those loops, you see here, the length of this closed loop is 6. The length of the sum of the length of these two loops is 8. Is 8. Here, the length of the closed loop is 4. The length determines the energy. Just imagine any loop that you can write down, any closed loop. Count the length of that closed path. The length gives you the energy of that system. And you can practically write down the corresponding contribution. And that the contribution to this sum, let's say, this is an overall factor. I can treat it separately. The contribution to this sum from that loop is just e to the power minus k times length of closed path, whatever that length is. So now just diagrammatically I can write down all the correction up to whatever order you want. And since k is very large, it will be enough to keep, let's say, the first 1 or 2 terms here. But then you see there's, on one hand here I have the high temperature expansion, which I wrote as sum of closed paths on my lattice. Here I also have, in the low temperature limit, I have another expansion of sum over closed paths. But there is an important difference though. You see here, the closed paths I wrote down are connecting the lattice sites. Here, the closed paths I wrote down is crossing the lattice links, if you like. Or they are connecting these points, not the lattice sites. Now let's again go back to the triangular lattice. That's a more interesting case. I have these lattice sites. I just imagine all the links connecting my lattice sites. So in the low temperature expansion, what I did was I just constructed paths connecting these lattice points. What I did in the high temperature limit was I considered the lines perpendicular to these links. I constructed my paths using these red curves, red paths. But you see, if you look at these points, they also form a lattice. They form a hexagonal lattice. The black dots form a triangular lattice. So basically what we had done is, in a sense, the low temperature expansion in the triangular lattice is the same as the high temperature limit of the hexagonal lattice, and high temperature expansion of the triangular lattice is the low temperature expansion of the hexagonal lattice. So these two lattices, well, I mean, you can generalize it to other square lattice also. These are so-called dual lattices. A square lattice is self-dual, in the sense that the dual of a square lattice is also a square lattice. And in fact, let's go back. We said that, okay. So here we made all these expansions. You see, up to this point, I make no approximation. This is exact. The approximation is when I say that, okay, at high temperature, V is small, so I can truncate this expansion at a given order. That is the approximation. In the other extreme, low T limit, again, up to this point. Now, this point is exact. This is also exact if you calculate all higher orders. It is valid at any temperature. Low temperature limit is only appears when I cut it over here. But that basically tells me that Q calculated at that time at T of one lattice is in fact equal to the Q of the dual lattice at the dual temperature. Well, what is the dual temperature? You see here my expansion parameter is e to power minus kappa. In the other case, this kappa j, in the other case I have V, or tangent hyperbolic, probably they have a lecture, tangent hyperbolic K star. So this is the relation between the temperatures in both cases, and let's go out. So that is all I would want to mention, at least so that you have heard about them.